Dear colleagues, dear friends, it's a big honor for me to introduce Professor Fojtik, a very famous scientist, a pioneer in the direction of laser ablation in water technology, and our big friend and professor of MEPhI University. And I think maybe nobody knows that in Europe there is a so-called little Nobel Prize, Fojtik Tigran Awards till 1918, and now Anton, please connect with Professor Fojtik, and we will listen to the lecture. Plenary. Okay. Anton, welcome. You are welcome to present.
Okay. Do you hear me?
Yes.
Okay. I shall share my screen. So now I must do that.
Okay, we see your screen.
Do you see my presentation?
Yes, half of them.
Is a full.
Yes. Okay, just is the full screen. So welcome.
Okay, can I start to speak?
Yes.
Okay, thank you. Ladies and gentlemen, it is a pleasure for me to introduce you our research at the NANO for biomedical, laser for nano, pioneering pulse laser synthesis of colloids. I would like to take you at a trip for a retrospective story, which can show you our research for every beginning, from early beginning up to the present time. But first, I must express my thanks to organize the committee that give me the possibility to present my lecture for this auditorium. So, do you hear me okay? Its voice is okay, please?
Yes. Anton, very well.
Okay,
yes, please
good.
Continue.
So now I would like to show you from the beginning. I must to show you what we're starting to do in the nanotechnology. So nanotechnology, you can see here the pictures. And nanotechnology is interdisciplinary branch of science which give the possibility to another sciences like biology, chemistry, mathematics, physics to participate inside in the matter and to use the results from the nano for their own application. Biology can find something good for the biology and use them, and then can call themselves not biology, but nanobiology. When these science participated inside in the nano, they have some advantage for their own application practically, and afterwards must to name so-called like biomedicine, biochemistry, biophysics, and medicine, biomedicine. So that is interdisciplinary branch of the science nanotechnology. You can see that I make something like a connection nanotechnology with colloid chemistry and alchemy. That is because I want to say that these people which start to make some very nice sciences in the Middle Age, that called the alchemist, was not stupid people, but was very clever. I only want to say that American cannot produce the atom bomb when not using the technology from alchemists, and that was fraction crystallization process. At that time was not diffuser, not centrifuge, for make the from the uranium take one isomer and another. That is not possible at that time for very, very quickly the centrifuge. That must be make crystallization. And this crystallization process was taken from alchemists, which make such a process already long time before, several hundred years before. So I want only to mention that our science here must have connection with somewhere where people was very clever and starting something like that. So that is only that I want to explain why I make connection between the colloid to alchemy, because the American project for atom bomb was connected with crystallization, fraction crystallization, which was processed to isotope, two isotope from uranium split for one and another, and concentrated in such a concentration that can use that for atom bomb. That is only to demonstrate where we are working and where we are our beginning somewhere. So now I would like to say why these science are attractive, why they attract to start to study that. What is the reason why they come there? They use that, but why? Why they come? What is motivation for them? And I want to show you that the reason why this science participated. So example is that very small nanomaterial object has unusually physical and chemical properties which are not known surrounding us. So for example, you have black semiconductor cadmium arsenide, you see, that is normally black. When you make it very small one in the range of the size about the nano, several nano, 10, 5 nano, they change the color. And you can see that here is a cadmium arsenide dissolved in the solution, and that is a very small particles, and that is increasing the size of particles. They increase also the color, luminescence color. There's a signal that something happened with the inside and the structure, physical and chemical properties in very small particles, because normally you can know only the black cadmium sulfide, but that is identical. Chemical doesn't change, only the size, and you have color effect. That is something which is something very interesting. And now you can see carbon. Carbon is a coal. You can use it like a black material in home. That is normally. But when you make it very small one, you see the red and soluble and the organic substances. So that is tremendously big, these changes. You can not see a normal what surrounding you, that carbon is red. But when you put small particles, they are red, really. And iron, ferro, you can see is yellow and soluble. Silicon is also not metallic, but afterwards yellow, has a strong luminescence and soluble in organic solvents. We have another one. Nanoceramic is a material which can prepare the nanotechnology, and that withdraw temperature up to the 2,500 degree. That is something no other material in the world has such a properties. That is something which can be used very, very, very good. Space Shuttle Columbia used that. A carbon fiber, that is a composite, which is a 14 times lighter than steel and 10 times stronger. That is effect. That is not possible to see and find somewhere material surrounding us. That must be prepared at nanotechnology and Kelvar. That is material which withdraw very strong temperature changes and very strong forces. So now you can see that is Columbia, which has and the wings here covered nanoceramics, because when come back from universe to the atmosphere, the temperature at the wings are about 2,000 or more than 2,000 degrees. And that is very dangerous. And it's happened several years before when it was space shuttle. And that is a cosmonaut. We're starting with that cosmic Columbia. And that was some accident. Pieces of ice from starting, they fall down at the wings here and broke the ceramics about the size 10 centimeter quadrat, the hole. When they started up, no problem. But when come back, temperature 2,000 degrees can damage all the wings, and afterwards all the Columbia was blown up. All 7 people die. That is accident, because here was a hole. Here was a hole only 10 centimeter. And that is reason why we must very carefully use that. Now you can see another possibility for products which make the nanotechnology and give to another application for practical. That is a Kelvar. This material which is withdraw, this is textile material, can withdraw the temperature up to 200-300 degrees, no problem. So that is for fireman, for firemen. It is good for the uniform and for the another application you can see here. And it is excellent, very good one. So you can see where are the possibility to attract the another sciences to participate it, because they are very attractive product when it's very small one, and technology, nanotechnology can offer that all. So now I would like to come to situation when all this nanotechnology start. And that is an institute in the West Berlin, where is known this institute like a Hahn Meitner. Hahn and Meitner. Hahn was a professor in Berlin and Germany, and Meitner was a woman from Vienna, Austria, working with him. And Professor Hahn received the Nobel Prize for the splitting the uranium, and that without that patent, never can be construct the atom bomb and atomic electric production. That was a patent or the discovery how to split the uranium, and that is the name of Hahn and Meitner, like a memory for him. He was working at the Berlin and this science in this institute at the beginning. So we was working at this institute a long time before the 1980. We was working there about 15, 14 years. And that was also the another scientists from Australia, Israel, India, Poland, Czech, Switzerland, and Russia. And we was working with a linear accelerator, 2 mega electron volt or 10 mega electron volt. And we use the linear accelerator to produce some new substances, new significant, very effective material for another application, for practical and bio and something like that. That was before the nanotechnology. We make that research before. It was called like catalysis or something like that, mainly technical application. And these people working top at that institute, and they working, and I working also with them, with a laser for production, something like now we call nano, that was some another, but it was some colloidal for catalysis. And best people which come there, like a top expert, that was a professor from Moscow, that was a professor Yershow, and that was leader for all professors which come from another country, because he know the best how to use that, because at that time, Russia was at the top of the science in this field. No other country can compete at that time with Russia to using the linear accelerators so good like Russia has experiences, because in the Russia that has a tradition long time from the Second War, and that people which are working at the Moscow at the linear accelerator, they practice and bring it in Berlin, and they was very top people. And I want only to say how it was starting. In 1980, that was Project Eureka. Euro-Union country at that time, that was not like Euro-Union present time. That was only the few people like Germany, Italy, French, and some other, but not too much. And Eureka give the project, open the project, which want to end domination of America and Japan in the field of the chip technology. At that time, 1980, that was possible to sign the information in computer or in telephone only in the level 1 megabyte quadrat centimeter. But at the Eureka want to ask, it's possible to make something to receive more possibility to register more information than 1 megabyte. And so director of the Institute, Henglein, asked me, Anton, we are working at the small particles for the catalysis. Can you prepare something which we can reach potentially to write the information higher level than 1 megabyte? So I was working with my group here at the Institute for several months, and we have results, and you can see that. That was the results we received. That was different signs of the particles, cadmium sulfate, like an example, that we are possible to make higher density for writing the information. That is in normal light, and when the ultraviolet, you see different color. So that signalize that size of the particles are different. So now you can see that at the normal light, you can see nothing, but it is soluble different particles. But when you see the ultraviolet, you see that big one is here, like a red or something like that. And it is changing smaller and smaller. Here is very small particles, it's a blue, and here is so small particles irradiated ultraviolet and cannot penetrate the glass because glass stop the light. Here is the particles. They have light, but so small that you cannot see because it is very short. So that is what we have, and we try to make analysis for the chemistry. We make a spectrum of that. That is a spectrum of the particles, which are big one here, and we can see that when is a smaller particles like this, must to be shifting that spectrum, the shorter wavelengths like that, and others must be here such. But unfortunately, we have not such. That was something which cannot explain. He was a pickle. You see that this pickle was at the spectrum, and we don't know what is that. At that time, nobody can answer that. So I go to the literature. If I see somewhere work where I can see that maximum, and I find the metallic ceramic material, plenty of people working in this field, and they have gallium arsenide semiconductor, but when they this material keeping at the very low temperature, minus 100 or the 150, they have superconducting properties, and that was very, very, very good for application, but they can do that only in the minus 100 degree. And they try 20 years to reach the level of the normal temperature, but they doesn't succeed it. And that is exciton. And when I find that, I say, okay, we have also the exciton. It is the same effect like here, you see. So we take the results and go to the international congress, and they present it. Or we have something which we have very small particles. We can have the size particles. We can register maybe at the display information higher than 1 megabyte, maybe 10 megabyte at quadrat centimeter. And that is something new, and we was very proud, and we presented such a lectures. And that people which are here, which was at the conference and make the ceramic material superconducting, they say, oh, yeah, you are very wrong, not understand the physics. You must go home and ask money from the school because you don't understand what is exciton. Exciton is possible to see only in the low temperature minus 100. And you say that you see that at the normal temperature? Oh, that is not possible. You must have some dirty. Go home, please, go home. Take money from the school, and that is not correctly. We are working 20 years and we cannot reach that. And you young people come something and show us that have an exciton at the normal temperature. So they send us they pick up us from the conference, and we go home. And at home, I was very frustrated and asked my colleague, quantum physics and quantum chemistry, to help us to explain why we have that. It is not dirty. It is very much time repeated, and we always have that maximum. And they try to explain us, and I show you the result. People which make the classical ceramics, they have exciton in such a reason. You know, I tell you here, that exciton is a level of here is exciton level, and that is a conducting, and that is only the 40 milli-electron volt here. And thermal vibration of the crystalline gitter is 60 milli-electron, 60, which is a normal temperature. Vibration of the crystal doesn't allow you to see that maximum here. That is neglected because vibration of these structures has 60 milli-electron volt, more than this one. So what is possible? To cool down the material minus 100, 150 degree, stop the thermal vibration, and afterwards you can see that here the exciton level when it is. And that is what you can see that is minus 100. So you can see that with normal temperature not possible because that is a vibration. And the second argument, here at the conducting band, moving the electron is about 5 millimeter, several millimeter or the 5 maybe centimeter for second when it is go 1 ampere. But in this level here, exciton level, mobility of the electron is 1,500 meters per second. You see that very big difference. Here at the normal wires, gold wires, copper or silver, the electron moving only the few millimeter or centimeter per second, and here 1,500. This big difference. That is the reason why this material have a superconductivity, and that must be at cooling minus 100 or the more degree. And what is with our small particles? We calculated, and the results are such. When we make a smaller particles, when smaller and smaller, distance at the exciton is more, prolonged this distance, you see. When its particles smaller and smaller happen, that is more and more prolonged. So at this very small particles, which is about 2-3 nanometers, 20-30 angstrom, that is a distance about the 500 milli-electron, half a volt. So we can see the exciton in this level at the normal temperature. That is the reason why we can see that in the nano. And that was surprising. And we make the publication. At that time was publication current content. That was not before the internet. That was this American journal. They make all the referee of the publication, all publication all over the world at the 1 year. And that was about the 1095, 96. That was more than 1 million every year. And they make collection of 100 the best results for 3 years. Several million publication. They make selection for 100. And our work, because it was some surprising and very high level knowledge of the nano or the quantum. And we have at the 32 places, you can see that here. You see, that is our work here. And that was very good satisfaction for us. And next year we go to conference and everybody accepted. Make congratulations to us. Excuse that we make a mistake because we don't want to believe that we have that. From that time, I could see that we received the money from the Eureka project, several $1 million, or at that time was Deutsche Mark, German mark. So we have enough money to continue in our research and the Hahn-Meitner Institute, and we have a huge money to make something in application, and we continue to make up to the end. And I want to show you what's happening. So now I want only to show you that is example where big particles cannot make a chemically effective. We use the water, which is from the factory which produces a paper factory. That is dirty water, and they try to clean it. And titan dioxide particles was predicted that can make it. But big particles don't make it because they have no enough energy overcross chemical barrier and make something which reduce and oxidation and some dirty things which is not needed to cleaning the water. But small particles make it. You see, very small particle, titan dioxide, several nanometer, have enough energy to make a reduction or oxidation of water dirty, and they make cleaning. After the 2 days, they clean all water, and the water can use again, or they put it like a drinking water because it was very clean. And what is a key, physical key, the experimental key? You can see that. When it is small particles like this one, the big particles, when it is big one, small band gap, has not enough energy to overcross barrier. But when you make a smaller and smaller particles, I told you that you receive the higher and higher energy, you see, and the very small particles is a reduction so level, so you can overcross barrier, and you can see the electron can go and reduce something in solution, and the positive hole also can go upper and make something. So that is a experimentally proof that small particles can do something very miracle, but big particles cannot do that. And that is a fact that they change the band gap. Okay, that is good. Everybody can accept that, no problem. But problem is to prove mathematically. And now I show you. That equation open door for all the nanotechnology. All nanotechnology are in these two equations. So with the energy of the thermal energy of the electron in the material, you can see energy, you can calculate it. And this energy you can take from Maxwell-Boltzmann, and you can put it to the Broglie equation here, and you can calculate it, what is the wavelength of the electron and the thermal and the normal temperature. But it is calculated about the 62 angstrom, it means 6.2 nanometer. And now it's situation, when you make the structure, which is 20 or the 50 or the 100 nanometer, doesn't change no physical and physical property. Coal is black. Semiconductor, arsen semiconductor, is also black. Nothing happened because the electron can freely move from all the place for all the structures. No problem for the electron. Electron can moving because they have a dancing place, very big one, and the electron has only the steps, dancing steps about the 6.2 nano. And when you make a smaller and smaller structures, you reach the size of the wavelengths of the electron. When you have the size of the material of the, when you have about the 62 angstrom or the 6.2 nanometer electron, now feeling very stressy. When you make it smaller, classical physics give you that electron must thermally leave the material. When the material is lower than the wavelengths of the electron, physically electron must thermal emission and go away. But in this case, the electron is very clever, don't want to go. they want to make and stay at the material, and they make very clever steps. They make a shorter wavelength to stay at the material, which is lower than his wavelengths and normal temperature. He make shorter wavelengths. You press him to higher energy. And when it is smaller and smaller, electron is clever, don't want to leave away, he make a shorter and shorter wavelengths. And what is that? When make a shorter and shorter wavelengths, must to increase the energy. And that is exactly what you see, that one. That is reflected, this equation. And that now, that is a possibility to make some application, and we call that we have this quantum particles, because at that time was not named nano and nanotechnology. We always make a small particles and makes, that is a quantum, because they open the quantum, you know. Here we can see the quantum, everything. So we say we have a quantum particles. But afterwards, when people want to use it, they ask, what is the reason that has such miracle physical and chemical properties when a very small one? No, this is because it's nano. How you make the nano? It's special technology how to make it. Why you call that the quantum particles? Why you don't say that is a nanoparticles, and technology which bring the nano is nanotechnology? And that was a time they're starting to speak about the nanotechnology and nanoparticles. And this was about the 2000, when people start to application results what we received before. And now you can see the nanotechnology give you this possibility to make very nice thinking. That is all is the nanotechnology. Now we can see that nanotechnology can make also the another properties. You can have here the glass, you put that these substances in the glass. Here is a bonding, this is suhydryl grease, that is aliphatic chain. And when you this precursor anionize, you can make ionization of that one. This is a minus, and here make it minus. So that is a hydrophilic. And when you change the charge here plus, that go there, and you can see hydrophobic. So with the changing the charging plus and minus, you can surface of glass changing from hydrophilic to hydrophobic. And that was only the showing example how it was manipulated, such a properties in nanotechnology. And sometime, you know, we have such an effect, and it was always saturated in technical application and biomedical application. And afterwards, there was not more possibility to make chemically small particles. There was not way how to continue. And I come to idea, maybe I can use the laser to produce those small particles, because laser focusing at the material, they bring very high energy, and I can evaporate it something and produce the particles. That people which are working with me and the Han-Meitner Institute, Anton, it is nonsense, because that pulsing, it is 1 or 2 pulse per second. At that time was such a laser possibility that was only very, very, very small repetition laser. So when you want to see something, you must use several hours pulsing, pop, 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 pop. 1 second, 1 pulses, or the 2 pulses, 1 second, pop, 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 several hours. And I ask, okay, Professor, Director Henglein, what do you think? Can we make it? Or Anton, try it. We can publish, even that is not possible to use practically, but we can try it and we can see what's happened. And it was something which was not project, which was what skeptic, but afterwards a surprise waiting us on the corner, you know. And that is first application. It is me, and that is Professor Henglein. He died in 2012, and that was the first application. And that is a paper which was published with the lasers, you know. And the lasers here is better show, because here it is not so example to good such look like this one. So this is a focus laser at the material that is a metal material or the coal or the some others, and they produce the particles here are cooled down, and the liquid water, acetone or the or some another, but must be without air, without oxygen, because oxygen can damage small particles. That is such. That is. And now you can see we can use that such that we can produce here from the gold, that is a gold, and we make it pulsing in different energy. 2.3 joule here repetition, and we have particle size 130, 140. That is here particles, and these particles have signal at the plasmon. That is a vibration electron on the surface of metallic structures, and they give a signal when particle is already metal character. When it is not metal character, there is no plasmon in that. So with a higher energy of the pulse, we have smaller particles. That is this one, and the smaller over this 20, and this is plasmon here. The particles, very small one, has no metal character, they have no signal for the plasmon. That is. And here is a nickel, and we have also that we make the coal here and make temperature about 2000 degree in the pulsing, and afterwards we can take this solution and make a chromatography, and we find the chromatography here, the substances which is here and this. That is a red one, I told you. That is a coal. That is a coal. And that is a product with a synthesis of very high temperature from the coal here. That is. And that was done in 993. But after the 3 years later, that was a people group which received, that was Kroto, and received the Nobel Prize for FLAMN. We have before, but we don't pay attention to make more about that. But Kroto working with a FLAMN more than 10, 15 years, and he really received the Nobel Prize. And this is experimentally published already 1993, and we have this proof that we have that, but we have no chance to receive the Nobel Prize. But we have another advantage. We can have this silicon, and the silicon make a small particles, and that small particles we then filtrated with millipore filter, 0.4 micron, and that is a particles without the solution after the filtration, and that is centrifugated or they filtrated over this filter, and that is a absorption curve, you know, that is absorption, and that is a size of the crystals or the small particles which are at the solution. And when you irradiate it 350, you know, here, light, you can have emission about 680, 700 at a red emission. That is a characteristic effect which now you can very easy find it, but at that time was surprising. And it is a crystal, you see, that is a crystal of one crystal here. This is size of 3 nanometers, 30 angstrom. That is individual silicon atom in the crystal. So we have possibility to make such an advantage, and that was published already, and that was some publication which nobody care about that, because that time nobody care about the technology which needs several hours to pulsing, pop, 3 hours on the morning, costed too much time, too much expenses, because laser was very expensive, and now you have only the little substances. That experiment was very good, only to make some publication, and everybody forgot that. Nobody cared about that publication. They forgot. But after the 25 or the 40 years, like now, change the situation. Because after the 25 years, new approach that was asking for make a purity, very clean particles without any ligands, because when you make the chemical preparing the nanoparticles. You make it in liquid from the that is a liquid of the gold, and from the gold you make the particles with chemical way, but always have a ligand which you need it for chemical preparing. Citrate. You can have also the acid, that is, and here is a citrate, here is a tannic acid, and all that as poison, like a poison. And that was now asking, we need something which prepare the nanotechnology particles, gold or the silver, or without poison, not that one. And that is only way possible to make it with the lasers. And when you have a lasers like that one, you see 10,000 times per second. That is example how we produce. This is a gold, and this is a red particles of the gold particles, small one. Now you see, we can several minutes and we can produce that. So that is, and that is publication, and that is possibility. And now you can see what is the mechanisms of that. That is a pulse of the laser at the material, the evaporated particles. You can see the particles, and it cool down the particles, and afterwards we can use the particles for that. That is way how we use now, and that is possible now to make bio application. And bio application, now you can see the publication papers was tremendously changes, and that is situation 2015, but now it's prolonged. Now it is boom. Everybody is speaking nano. Nano is miracle. Nano is something excellent or something like that. But this starting slowly from that time, and now you can see that bioconjugation nanoparticles, it means at the particles you can contact another molecule which can be used for application. Like a transportation is gold particles, and conjugation is something enzyme or something like that, and you can transfer it to for biology or something like that. And the bioconjugation is better for the laser prepared particles, that is a laser particles, and this ligand are 4 times better than the chemical exchange. And there's a chemical particles, and that is laser particles. So laser particles and structures is much more effective and better. So that is example, what is a profit of now? Pulse technology against the classical chemical technology, that is. And now I ask you the Alzheimer diseases. Now you can see that Alzheimer is a neuron, can each other contact, and when they contact each other, they can remember. When they, as a plaque, that is from amyloid, which is from the neuron, that is a polymer which stop vibration and the contact between the neuron, and you lost the memory. You don't know where you give the key, and afterwards we must to destroy that polymer. We make the nanoparticles, gold, put there something like a binding site, and we take the polymer, that is a polymer which come here, and this is a protease enzyme which can split the polymer and the pieces. You see that? You see that is. And now you split the glue and the brain, and again can be this neuron can touch again, and people can remember. That is better. We cannot completely Alzheimer diseases complete away, but we make a progress in that one. So that is experimentally in biology. This is also in biology. I don't want to go to detail, but biology is also using such a process. Now you can see the experimental. We can make it experimentally at the hospital, at the Berlin hospital. That is a reason. You see that. That is molecular structure of the glue between the neuron down. That is a reason why afterwards we can help for the Alzheimer, and that is experimentally. You see
Anton,
that
I'm sorry.
that is a possibility to make damage the polymer, and that is only the experimental results. I don't want to go to detail, but you can see very evidently that we have possibility to cut down the size of the polymer, and it is such. And that is only the polymer.
Anton, I'm
yes.
sorry.
Oh,
yes.
Okay, I go that. And that is possibility to make also the Parkinson, and that is a possibility, and that people has an electron, the needle, and they put here the voltage, and that voltage, and they stop that trembling, that stop that. And we have nanotechnology cover this needle over the platinum iridium, and we make it, and that was succeeded, and that was what we have possibility to make that. So that was something which I want to tell you. That is example how we make progress in such an application in biology. I mean, that is all a cover. I have no more time. So I would like to thank you for that application and what I show you. I have something more, but next time, maybe more time. No, thank you very much. Thank you very much. That is all.
Anton, thank you very much for your wonderful presentation. It's very interesting and historical review and new results. Thank you. A lot of thanks. We have time for questions, please. Questions? Any questions? So I'd like to ask Anton, what do you think not in biology, not only in biology, but what do you think in other fields for applications?
Another field? Okay,
yes.
Another field. Okay, wait a moment. You might do that. Another field is this one. That is registered of information is a disk and the memory, and nobody can read it. And that this nanotechnology can prepare the particles which can show us where are the information. That is information and this disk, and that is technically application of laser application, pulse laser. We produce a small particles, magnetic, and they can see the information which you cannot see that. That is digitally see. That is information, and the disk in the memory, we can send it. And that is a possibility to make better printing the finger 10 times more detailed than classically. That is criminalistic. And also the testing material against that. You can make a gyroscope. You can have nanofluid for the transporting. We have plenty of application technically. We have no time to explain that. But in this way, that is a technically, we have huge application, and it was plenty of application done. I have that lecture I have for the student. Now I want to only say your question that we have also the application, not only medical, but we have also huge application in the technical field. That is okay.
Thank you. A lot of thanks. Please, would you say, okay, one question more?
Yes, thank you. Very nice, impressive talk. And I have a question related to productivity. So at your time, you mentioned it was a few pulses per second. Now it's about a megahertz pulse repetition rate, but still I think people from chemical community do not believe that productivity of laser synthesis is enough for practical applications. So what is your expectation about expectation?
You mean?
I mean the issue with the productivity. So people still believe, I think, the productivity of laser synthesis is too low to go into the real practical application. So please comment this.
Now it's produced. You can use the laser which has more than 10,000 per second, maybe 20 or more, and they produce the particles which are very small one, gold particles. Let's say.
Anton, we have some problem with another material like boron. Now you know that
boron.
You know that
another
we deal
material.
With
that is a problem.
Not good. Yes, the velocity of production.
When it is chemically not stable, it is problem. Yes, it is problem. That must be the solution where is it protected, because some bore or some other metal or some other individual has not stability and a solution, and that is something problem. It is true.
Okay.
You must to find how it is because normally we is very good and no problem there.
Yes, we will discuss with you. Yes, me myself. Okay.
Okay, no
So-
problem. But when it is problem in the chemically, that is also problem for the
Yes,
pulsing, because
yes.
pulsing is chemically and physically connected with the material. Okay. That
Okay.
is.
Okay. Dear colleagues. Okay. Just one questions more.
Yeah, thank you for such great presentation. I'm not a specialist in the biological applications, and I wanted to ask about the safety of these mechanisms of nanoparticle fabrications and in biological applications. I mean that it's not fully safety, as I understand correctly. Can you comment it?
I don't understand exactly what you mean.
Like it stays inside
please,
our body.
You can speak. You can say in Russia, please. Just
You
say.
can say Russia.
Okay.
Понимаю по-русски, но говорите по-русски, что вы
Хорошо,
хотели.
да, спасибо. Я хотел спросить про именно безопасность этих наночастиц в применениях биологии. То есть, насколько я слышал, они остаются внутри тела, и их нельзя вывести, и собирают на себя там разные белки, и только наоборот появляется опасность появления вот этих болезней, Альцгеймера того же и так далее. Но это просто, опять же, я не разбираюсь, мне интересно вот услышать ваши комментарии, да, спасибо.
Эти проблемы очень большие, я знаю. Это решится, да. Потому что некоторые наноструктуры очень токсические, but you must to compare. If you want something to do or not to do, we have some particles against the cancer. And these particles are not 100% acceptable. Maybe some 90 or something like that. But now you must decide it. Do you want to have a cancer or do you want to kill the cancer? That is obviously the 10%, but people must to decide it. We have also a possibility to kill some other possibility, as a virus. And when we have a virus, we have possibility to kill the HIV virus. And that is a process which give you risk, but you can ask the risk. Risk is not 100%. Risk is about the 40%, but 60% successful or the 70%, that when you have a HIV virus, we can liquidate the HIV virus in your body completely, but risk is 30%. And now you can see that because we are not possible to make it at the normal hospital because hospital doesn't allow that. You must to have agreement from the government or something like that. But we make it in the other countries. I don't want, let's say, another countries, which is no problem. And there is a patient which is dying. They have about 1 year before they die, and they have HIV. And they say, oh, I have a HIV, I totally shall die. And I say, I am not allowed to tell you because that is not 100% sure. Doesn't matter. I live only 1 year. I need the risk. So we can make it. So that risk is such that we can put all the blue outside, take HIV virus away with nanoparticles and clean water, clean blood, give back to the body. That was tested in the hospital, but was not allowed to make it for the people. But some people demanded, okay, that is a risk. So risk study about the nanoparticles for the human body is a big progress. It's a very big laboratory try to do that. I know that. But the people which are working is understand that something is very dangerous. Let's say linear carbon layer now is a miracle physical properties, but dangerous, very much dangerous. The layer, monolayer of carbon, you know, or that is very dangerous because the powder of that immediately you have cancer as a lunga. No possibility to dissolve it. Absolutely not, because it's carbon. That is very toxically. because that is toxically when you take it like a powder. In water is not toxically, but that is a subject which people now very carefully criticize, you know. I did this answer for the question if the nanoparticles are toxic or not. Some are toxic and some are not toxic. But now the progress is the carbon layer, very toxic, absolutely toxic. But must be very carefully. That is my question and answer. I thinking that the risk is always lower than profit. Profit always very good.
Thank you very much.
Можно я немного тоже, Антон, я немного тоже прокомментирую, потому что, конечно, наиболее перспективные материалы нано в медицине будут биоразлагаемые, которые потом естественным путем выводятся из организма. Но надо понимать, вот, например, есть рак печени с прогнозом там месяц-полтора, а использование вот наночастиц сферических, которые закупоривают питание в сосудах, вот, приводит к тому, что человек без боли живет 1,5 года. Люди даже считают, что они вылечиваются, они идут на это. То есть нельзя,
это правда.
Да, нельзя паллиативно, это называется паллиативной медициной, да, облегчить качество жизни больного человека, вот, и продлить ему жизнь. Поэтому
это жизнь, да, я знаю,
да,
это всегда
Антон,
так.
Спасибо. Коллеги, есть еще вопросы, потому что блестящий доклад, вот, или мы поблагодарим нашего замечательного ученого. Антон, будь здоров, пожалуйста. Вот,
спасибо.
И мы тебя ждем в Москве и в Ленинграде. Мы тебя будем ждать в Москве и в Ленинграде, хорошо?
Хотел бы, да. На лучших условиях, да, хорошо.
Да.
Но все. Спасибо, да, все.
Да, мы тебя любим, да. Все, спасибо большое. Вот, я передаю, да, Галине Викторовне.
Okay. Dear colleagues, let me introduce our next sponsors from company NPP VOLO. Where is? Yes. This is our friends, our postgraduate students. Yes, please. I don't know, we have a microphone there.
На русском должны? Вроде как. Просто не репетировали на английском. Добрый день. Извините, что по-русски. Ну, презентацию готовили на русском, поэтому оперативно изменить ее на английский язык не было возможности. Так, мы представляем нашу компанию NPP VOLO. NPP VOLO является частной компанией, основанной в 1991 году, более 30 лет назад. Основана она была сотрудниками Государственного оптического института. И основной ее вид деятельности – это выполнение научно-исследовательских опытно-конструкторских разработок, направленных на создание новой лазерной техники и лазерных технологий для здравоохранения и различных отраслей промышленности. За последние 10 лет было выполнено сотрудниками компании более 120 неокр, из которых около четверти являлись инициативными. Получено 9 патентов на изобретение. Большая часть прибыли компании направляется на инициативные работы и исследования в области лазерных технологий. Кажется, не работает. На предприятии трудится более 50 сотрудников, из которых 35 человек заняты исследованиями и разработками в области лазерных технологий. Научный потенциал коллектива состоит из 2 аспирантов, скоро будет, возможно, 3, 5 кандидатов технических наук и 2 члена коллегии национальных экспертов стран СНГ по лазерам и лазерным технологиям. Структура компании представлена научно-исследовательским отделом, состоящим из 3 секторов. Сектора оптических и оптоволоконных систем, сектора медицинских лазерных технологий, начальником которого я являюсь, и сектор промышленных лазерных технологий. Сектор оптических и оптоволоконных систем. Основная деятельность его направлена на создание осветительных лазерных систем, например, индикаторов на лобовом стекле для воздушного и наземного транспорта. Также это разработка и изготовление волоконно-оптических световодов по требованиям заказчика для медицинских применений, для промышленных применений. Световоды представлены серийно выпускаемые, они имеют следующие типы коннекторов. Также можем разработать специализированные коннекторы по техническому заданию. Ну и понятно, что также имеются различные толщины, диаметры оболочек и типы внешних защитных покрытий. Сектор биомедицинских лазерных технологий, его деятельность направлена на разработку новых биомедицинских лазерных систем, разработка в рамках разработки этих аппаратов происходит разработка компьютерных моделей, работы ведутся по автоматизации управления параметрами лазерного излучения в ходе лазерного воздействия. Серийно выпускаются хирургические лазеры с различными длинными волн, лежащими от ультрафиолетового до инфракрасного, 1500 нанометров, терапевтические лазеры и также световоды для медицинского применения. Вся медицинская продукция, выпускаемая НПП ВОЛО, имеет все необходимые сертификаты и регистрационные удостоверения. Вот. Следующее подразделение про сектор промышленных лазерных технологий расскажет сотрудник этого сектора, младший научный сотрудник Зhurba Danila Владимирович.
Уважаемые коллеги, я продолжу рассказ и сейчас буду докладывать про наши инициативные разработки, которыми занимается сектор промышленных лазерных технологий. Одно из таких направлений, которым мы уделяем большое внимание в данный момент, это подводная лазерная резка. Она предназначена для разделки, соответственно, металлических конструкций в тяжелых условиях подводных и отличается, например, может применяться для аварийно-спасательных работ, для демонтажа конструкций, для резки элементов атомных реакторов. Основные преимущества этой технологии заключаются в высокой скорости и качестве резки, безопасности для человека и для окружающей среды, низкому энергопотреблению, удобству в использовании и высоким сроком службы источников, отсутствием расходных материалов и, что немаловажно, возможностью автоматизации. Мы уделяем внимание одновременно и применению в ручном варианте и в автоматическом варианте. Параллельно разрабатываем 2 способа применения. И как мы видим здесь на слайде, глубины выполнения работ в ручном варианте до 50 метров, а все, что свыше 50 метров, делается уже исключительно автоматически. На данном слайде представлен общий вид комплекса, каким он был сделан уже в 2020 году. Сейчас мы одновременно с отработкой технологий приемов доработки рабочего манипулятора для повышения качества резки и увеличения ширины реза за счет газодинамики, мы одновременно и улучшаем технико-габаритные характеристики оборудования. Появляются новые лазеры, более компактные, соответственно, и установка у нас становится более компактной и мобильной. На данном слайде представлены варианты манипуляторов, с которыми работает водолаз. То есть если он режет не просто вручную рукой ведет, для него есть возможность упростить работу с помощью либо режущего трактора, либо режущей линейки. Также на слайде представлены технические характеристики аппарата, вес и размер. Следующее важное направление, которым мы занимаемся, это технологии обработки поверхности стальных изделий для улучшения их свойств. Это антикоррозионных свойств. Также занимаемся ударным упрочнением, термоструктурированием и закалкой. При антикоррозионной обработке первым и важным этапом является лазерная очистка поверхности, так как от его качества зависит эффективность дальнейшей обработки. И очень важным в данном направлении является технология очистки от окалины, потому что большинство металлопроката и металлоизделий, они покрыты окалиной, которая ухудшает коррозионные свойства и не позволяет выполнить дальнейшую эффективную обработку. Здесь у нас уже большие наработки по развитию новой технологии лазерной очистки от окалины, на которой получен патент, разработана специальная сканирующая система, позволяющая эффективно выполнять данную очистку. Следующее важное направление наших разработок – это применение лазерных технологий в топливно-энергетическом комплексе. Сюда стоит отнести технологии лазерного бурения, лазерное бурение угольных пластов для дегазации и генерации синтез газа, а также лазерное бурение нефтеносных пластов, в том числе горизонтальных скважин для повышения нефтеотдачи. Также в данном направлении стоит развивать технологию лазерного вскрытия обсадной трубы для замены традиционных технологий, которые обладают рядом недостатков. Здесь уже проведены эксперименты и показана высокая перспективность данного направления. То есть с большой скоростью можно формировать протяженные каналы более 200 мм, что обеспечивает, собственно, эффективное вскрытие обсадной трубы и приток нефти для ее добычи. В этом же направлении есть технология, которой мы занимаемся, лазерной очистки нефтекомпрессорных, насосно-компрессорных труб от отложений, эксплуатационных отложений, ржавчины. Здесь мы разработали установку лабораторную для выполнения и отработки этой технологии. Вот, содержательная часть у меня на этом закончена. Хотелось бы особо отметить, что компания готова к сотрудничеству с заинтересованными компаниями, молодыми исследователями. В данный момент мы ищем научных сотрудников, инженерные кадры и программистов, электронщиков, а также мы уделяем большое внимание подготовке научных инженерных кадров, взаимодействуем с университетами, в частности с ITMO. Очень активно взаимодействуем, приглашаем всех студентов к нам на практику, стажировку, выполнение научно-квалификационных работ. Соответственно, мы готовы к сотрудничеству и помогаем молодым научным сотрудникам внедриться в нашу компанию. Спасибо.
If there are any questions to VOLO, so you can ask them on their stand. And we have very important technical announcement right now. We're gonna tell you about the publication on optical and quantum electronics, and Professor Vartanyan can probably tell us more about this.
So, all participants of the conference are invited to send their papers to the following public journals. Karataev have already said about Journal of Optical Technologies, and I would like to say about the optical and quantum electronics. So you see the links to the special collection which will be collected by the journal from the papers of the participants of this journal. Okay, so you can go directly to the by these links and submit your papers. All who was in the conference who presented are invited to submit to this collection. Okay, so this is a guest editors of this special collection, and an important thing is when you come to the journal page, you choose, excuse me, oh, this is, so you choose these collections. I cannot show anything, but you see the collection. If you are submitting to a collection, please select it below. So this collection is already open for submissions, and it is only for us, for the participants of this conference. So after that, you just follow the rules of this journal. And finally, I would like to ask you to help me to serve for this purpose. And here's some suggestions for the good referee suggestions. Okay, so if you do that, it will be easy for me to choose the referee, and the process will start earlier. And finally, I would like to say that all papers that will be accepted by the editors will appear on the site immediately. You should not wait for the collection of all papers there. As long the decision by the editors is made, the paper will go to the publication process. It takes 1 or 2 weeks, and it will be on the list.
First of all, можно по-русски?
Да, конечно.
Китайцам, наверное, все равно. Квантовую электронику выкинули из белого списка. Это правда?
Никаких комментариев. Понятие слышу первый раз от вас.
Ну вот, к сожалению, это так. Если ничего не случилось. И второе. После у нас ДОИ будет, можно это использовать для отчета в РНФ?
Несомненно. Это журнал, издающийся Шпрингером. Как только он появляется на сайте, у него есть, у вас каждой статьи в отдельности будет свой ДОИ.
То есть мы посылаем, она проходит рецензию, и не дожидаясь выпуска, мы получаем уже ДОИ, да?
Вы получаете ДОИ, как только статья размещается на сайте. Размещается она немедленно после принятия решения
о публикации, да?
Да. Там 4 приглашенных редактора. Один из них это член, постоянный член редакционной редакции этого журнала. Ну а 3 остальных вы знаете.
Спасибо большое. Это большое дело.
Какие-то еще вопросы есть? Если у нас вопросов нет, я тоже поднимусь. У нас сегодня состоится церемония закрытия. Мы всех на нее приглашаем. Церемония закрытия состоится в 16:10, начало сбора вот в этом же зале. Очень просим всех, кто участвует в сессиях до церемонии закрытия, быть оперативными, не нарушать тайминг, так как после церемонии закрытия у нас состоится торжественный банкет, который пройдет на корабле. На университетской набережной мы собираемся в 17:50, поэтому у нас не так много времени будет на то, чтобы закрыть наш замечательный симпозиум. Я думаю, что на этом данную сессию можно завершать. Я благодарю Университетская набережная, 13. Но мы отсюда пойдем, поэтому как-то будем идти подольше, но добраться на транспорте можно довольно быстро. Отсюда пойдем какими-то группами, скорее всего, ну, не организованными, потому что у нас сегодня еще репетиция алых парусов, и могут быть проблемы с организованными группами, поэтому в любом случае можно подходить ко мне, можно подходить к Галине, к Вадиму Павловичу, мы все будем двигаться отсюда. Если нету ко мне никаких вопросов, тогда я еще раз благодарю наших замечательных председателей заседания. У нас сегодня просто восхитительный состав наших ученых. Спасибо большое Ирине Николаевне Завестовской, спасибо Галине Викторовне Романовой. И тогда можно, наверное, закрыть это пленарное заседание, последнее на этом симпозиуме. Всем спасибо.